This is learning target 3.4. I can simplify the quadratic formula to represent exact solutions. The previous learning targets have all been about simplifying the quadratic formula. The other skills in this learning target are all background skills for being able to simplify such an expression. For example, you might receive an expression as x equals negative 12 plus or minus the square root of 288 over 6. I did not give you an equation because that is not a focus. We are working on simplifying the expressions. So based on the skills we have two methods we can use to simplify that square root of 288. If you notice, the number underneath the square root is 288, which is a positive number. From the last learning target, hopefully you know that because it is a positive number, there are going to be two real solutions. I'm going to use both methods to simplify that square root, so you can pick whichever one you prefer. The first method, you know, and you can figure out what perfect root goes into 288. For example, I know that 144 goes into 288. So 144 times 2 gives me 288. So I can rewrite my expression. Instead of the square root of 288, I've got the square root of 144 times the square root of 2. The negative 12 and the 6 on the bottom just stay where they're at. I know that 144 has a square root of 12. So again, I'm going to rewrite my expression with a 12 on the outside and a 2 left over in the square root, because 2 does not have a square root and it cannot be simplified anymore. The second method takes up a bit more paper space, but that's okay. You've got the square root of 288. If you're not sure if 144 goes into it, or if 144 is a perfect square root, what you can do is over here on the side, I'm going to just start figuring out some factors. I know that 288 is an even number, so I'm just going to divide by 2 until I can't divide by 2 anymore. So I've got 2 and 144. Again, 144 is even. So 2 and 72. 72 is even, so I'm going to do 2 and 36. 2 and 18. 2 and 9. I need some more space. And then 9 is not even, but I do know that 3 times 3 gives me 9. So I can look at all these factors. I'm looking at all the small ones that could not be broken down anymore. And as the example said earlier, I'm looking for the pairs. So there's a pair of 2. So I'm going to rewrite my negative 12, and I'm going to put the 2. Here's another pair of 2's. I don't have another pair of 2's, but I do have a pair of 3's. So that means I can pull out 1, 2, another 2, and a 3. What's left on the inside is what I have left over. So there's a square root of 2 on the inside, all over 6. I can now simplify, go back up here and simplify that 2 times 2 times 3. 2 times 2 is 4, 4 times 3 is 12, so I end up getting the exact same answer no matter what method I choose. Now these are not completely simplified. I have just simplified the square roots. Something else you have to start to look at is you've got to start to look at these numbers that you have. It's kind of like a 12 over 6 and another 12 over 6. I need to simplify all 3 of those pieces. So think about a number that goes into 12, 12, and 6. Hopefully you're starting to see that the number 6 does. So if I take the negative 12 and divide it by 6, I would end up with negative 2. That 12 divided by 6 is 2. That square root stays there because there's nothing I can do with it. And then 6 divided by 6 is 1. If you look at the second method, we'll clearly get the same thing as we had the same answer. So our final answer for this problem, completely simplified, and in exact form, no decimals, no approximations, is negative 2 plus or minus the square root of 2 negative 2 plus or minus 2 times the square root of 2. The reason we want an exact answer is anytime you see a math problem that does not have a real-world context, you want to have an exact answer. We are not going to do approximations. Approximations are only useful in real-world situations. So there's one example. Let's do another. For example, pretend like you had an equation. I gave you a quadratic formula. Or I gave you a quadratic equation, and you started to use the quadratic formula. And this is what your quadratic formula simplified to be. 6 plus or minus square root of 48 all over 2. Again, we can use either method. Doesn't really matter. For method 1, I'm going to think about the numbers that go into 48. Well, I know 6 and 8 go into 48, but neither of those have a perfect square root, so I can't really do much with those. I also know that 24 and 2 go into that. But again, neither of those have a perfect square root. So the first method might take some trial and error. We can try the numbers, let's try 3 and 16. Because I believe 3 times 16 is 48. So you can check that on your calculator if you need to. Alright. Which one of those has a perfect square root? The 3 or the 16? Hopefully you said it was the 16, and what is the square root of 16? That is 4. So you've got 6 plus or minus 4, square root of 3, all over 2. And again, that's using method 1. Using method 2, we're going to break 48 up until we can't break it up anymore. So let's do 2 and 24, 2 and 12, 2 and 6, 2 and 3. And again, I'm looking for pairs. So let me rewrite the 6. There's a pair of 2, so I can pull out a 2. There's another pair of 2, so let me pull out another 2. And what's left over is a 3. That is what goes under the square root. Simplify that 2 times 2. 2 times 2 is 4. Square root of 3. As you see, we receive the same answer again. Now again, if you think back to the last problem, I need to check to see if I can simplify. I won't always be able to simplify here, but I always want to check, just like with the square root. Sometimes you'll have a perfect square root, sometimes you'll have one that you can't simplify. But you always want to check. Is there a number that goes into 6, 4, and 2? Hopefully you said 2. So what's 6 divided by 2? That's 3. 4 divided by 2 is 2. The square root gets left alone. And then 2 divided by 2 is 1. I have a 1 on the bottom again, so my final answer is 3 plus or minus 2 to the square root of 3. Alright, let's try another type of problem that's very similar but a little bit different. Again, pretend like I gave you an equation that was quadratic. It was a symbolic problem, so there was just an equation. They asked you to find the roots, the zeros, or the solutions. You proceeded to use the quadratic formula, and this is the type of expression you would end up with. X equals negative 15 plus or minus the square root of negative 75 all over 10. Now hopefully you notice that this has a negative number under the square root, so it has a negative discriminant. As you recall from the last learning target, a negative discriminant means it has 0 real solutions, 2 complex solutions, or 2 imaginary. All 3 ways are correct, so please be sure you understand them. Because this has a negative under the square root, I need to also think back to what I equals in the previous video. I know that I equals the square root of negative 1. So anytime I see a negative under the square root, if I want to pull it out, all I have to do is pull out an I, then I can work with the square root as I normally was. So there's that negative. I'm just going to pull out an I, and everything else is going to remain the same. That I is the only difference because that was the negative. Now I have a positive 75, and I can proceed as I have been. So again, if I like to use method 1, I know that negative 15, 75, I know is 25 and 3, because 25 times 3 gives me 75. And then I have a 10 on the bottom. The square root of 25 is 5. So I'm going to write 5, then the I, and what I have left over in my square root. Method 2, and you don't always have to pick 1 or 2. You don't have to stick with them. You can alternate. If you like 1 for this problem because you know 25 times 3 works, it might be easier. For larger numbers, the second method might be easier. It all just depends on your preference. I'm going to come over here and I'm going to break up 75. Now it's not even, so I can't use the method I've been using. So let's try 3. I know 3 times 25. And 25 breaks up into 5 times 5. So there's my pair. Don't forget my I. And I can pull out a 5 and put that in front. And then the 3 stays inside, because that's what I had left over. And then there's a 10. If you notice, I do have the same answer both times. Now I need to work on simplifying. Is there a number that goes into negative 15, 5, and 10? Hopefully you know that there's 5. So negative 15 divided by 5 is negative 3. 5 divided by 5 is 1, so you can write the 1, or you can just leave it as an I. And then 10 divided by 5 is 2. So either way of writing it is correct. You're probably going to see it written without the 1. But if you put the 1, you are not incorrect. You just need to recognize that it's implied. So the process is pretty much the same when you have a negative discriminant. You just have to identify that negative, pull that out with an I, and then continue simplifying as normal. Let's try one more example before I send you on your way to practice with your formative. Again, pretend like I gave you an equation. It said find the roots, zeros, or solutions. And when I simplify my quadratic formula, I end up with x equals negative 5 plus or minus 111 all over 3. Let's make it a negative 111. So as in the last problem, you know it's a negative discriminant, so it's going to have 0 real solutions, 2 complex or 2 imaginary. I want to identify that negative, and I want to pull out that negative by making it an I. That way I have a positive number to work with. The square root of 111. Now you can play with this number for quite some time, but hopefully you recognize off the bat that 111 is a prime number. It does not have a nice square root. It does not have a whole number square root, nor does it have any numbers that go into it that have square roots. So my final answer is actually negative 5 plus or minus I, 111 all over 3. So there wasn't a whole lot of work to do with this problem, but I wanted to make sure you saw that you don't always have to simplify. It's not always possible to simplify. So go ahead and try your formative. Hopefully you'll be able to do these, and good luck.